said already. And
Dora can ask about these choices. V function, which you say you take density, you can take any functions.
sorry, I cannot follow.
The function V,
W.
W.
Okay. Well,
So you say you take density for simplicity, not to have the
proportional to densities. You may, perhaps other functions could help you to.
Yeah. How do you answer? I guess referee can always ask you, okay, how do you justify in terms of performance, not in terms of simplicity, the choice of this function?
Well, if you don't take something to cancel the denominators, then you will not get a consistent test, except imposing very, very strict conditions, because you have to trim the denominator. The problem with Nadar-Watson regression is that the denominator, when it's close to zero, you cannot get it bounded away from zero. So it's very, you cannot get uniform convergence on the whole line for Nadar-Watson. So making something proportional with f, you avoid denominators. So if you trim in order to not to weight, of course you may put some conditions on the design such that the density is bounded away from zero and the x's are compact and things like that. Okay, but remember that the idea we are using is to make projections. So even if you impose that the design of x, take for instance a uniform, it's uniform on 0, 1, or on a cube. When you are making projections, so projection it does no longer have a density that is bounded away from 0. So you get stuck with this. So what you have to do is, even if your initial design x is bounded away from 0, you have to trim inside the cube in order to be sure that all the projection x beta or x gamma have a density bounded away from 0. And when you trim, in fact, you are not checking all the x's. So you are no longer consistent.
Even if the trim dimension.
Yeah, but this is
inconsistent.
Probably yes, but then you introduce a lot of technicalities that are very easily avoided by taking a W function that is proportional to the density.
Yeah, but maybe by making this job you improve the performance of the test.
I don't know. I would say it's not obvious. You just complicate your life. Maybe theoretical. I don't know. Let's try to do the last part. It's about functional responses. So, as I said, in functional data analysis, it may happen that both the response and the covariates are functional. For instance, as I said, you may have curves and images, or images and images, or curves and curves, or whatever. Maybe you put a relationship between them. And many models were developed. Of course, one more time, by simple extensions of what people usually do in multivariate analysis. So we will see with very, very few modifications that all what we said could be adapted very easily to this case. Extremely easy, in fact. So, of course, the steps are the same. We need a fundamental lemma, and if we need a fundamental, after we have the fundamental lemma, this now writes under this form. Previously, it was only u times this expectation, if you remember, yeah? But now, u is functional, so I take a scalar product between these two quantities, that are equal to 2, and we project for any gamma. And just to vary a little bit things and not to do exactly the same, let's not work with this, but with the transformation of this. And let's transform it exactly by the distribution function. Well, for people used with smoothing, we will go now from kernel smoothing to nearest neighbors, which will have very nice properties. You will see in a minute. It's a kind of magic with this projection site idea. So this is the fundamental lemma that prepares everything for the functional responses. Of course, with the V version, everything goes exactly the same way, because in fact, it works on each component in the decomposition of U. So then, of course, the U statistic to be used, it's very much like before, with very fundamental changes. Instead of Ui, Uj, you take the scalar product between Ui and Uj. So this is very easy to compute. And now, instead of xi gamma xj gamma, you take f theta of this. But of course, you don't have the f theta of this. You have only an approximation of that. So let f gamma n be the empirical distribution. F gamma n be the empirical distribution of the sample So f gamma n is the empirical distribution function of the sample x1 gamma, xn gamma. So instead of working with x product with gamma, we'll work with the order statistic for this sample. This is nearest neighbors story. So everything will go exactly the same. The steps are exactly the same. Now you can easily understand if the central limit theorems and all the stuff was done conditionally on axis, the fact that you change things here will not change very much the story, because since this fn function depends only on axis, does not depend on the use. Okay?
Excuse me, can you repeat, why do we need to use this f function here again?
Well, this is another idea. Instead of using usual kernel smoothing, you're using, let's try to use an alternative smoother, the nearest neighbors.
Ah, okay.
And everything was prepared with this transformation here. And since you don't have this function, you use the empirical version of that. And this is exactly what people usually do when using nearest neighbor smoothing. Because what you do is, this is the order statistic for estimating the function in xi. You just look at the other observations that are far or not on the line from xi. Okay? It's different from it's like, in nature it's the same because it's still a kernel smoothing, but it's based on the proximity given by this closeness of the observation given by this order statistic. The variance estimator now, except if you want to estimate the variance of this, let's take the square to make simple. No. Otherwise, might be more. Yeah, could be, but. So the statistic is the same. So I will not. The steps of the proof are exactly the same. We have to control the increment of the in-process, then to prove the central limit theorem, and do consistency and things like that. The first surprise we have with this new approach, using nearest neighbors, comes from the order of the U process. If you remember, on the previous slides here, it was a p to the power 3/2. Now it's only p. And it was a very nice surprise for us. And also that the proof of this order is much more simple. You don't need a U process theory for that. In fact, you only need concentration inequalities for U statistics and a very nice combinatoric lemma. The combinatoric lemma tells you the following things. So one of the things that we need to understand how it behaves is this story. Yeah? This is what I said. If you know the increments of this process, then you can understand how to penalize with gamma alpha and everything is okay. Good. This is a continuous. This is a continuous set. Okay. But now remember how. So what usually people do is just cut these sets in small sets, and locally they use an approximation, and then they count the number of small sets, and they get the order of the supremum. But let's remember how things were defined. You use this fnxi, fnxj. What are the possible values of these quantities? 1 over n, 2 over n, 3 over n, and so on, n over n. These are the only possible values. And how these values will be determined? These values depend how the sample gamma is ordered on the line. So this matrix here, it's exactly the matrix K I minus j over nh up to permutations of rows and columns. It's exactly the same matrix. So I feel that you will like it because this is deterministic. So for central limit theorem and for bounding all the terms, you only have to study this, because bounding terms with central limit theorems and concentration inequalities depend on the norms of the matrix here. But the norms of the matrix here will be exactly the norms of the matrix here, since these two matrices are only different up to permutations of lines and columns. So the spectral norm and the Frobenius norm will not change. So the behavior will be exactly the same. And this is a very nice feature of near neighbors, idea. And of course, now it's possible because we brought everything from p-dimensional space on the real line. And on the real line, you get this matrix. Easy.
I still have a small question. So if you're, in your original problem, x is random,
Yes.
you transform x design in the distance matrix.
Yes.
And then you look at the neighbors.
Yes.
If they are deterministic, you have unique transformation.
Yeah.
But if x are random, it could be that the 2 points which are close in one realization becomes not close in the other realization because they are random.
Yeah.
And this means you have additional random mechanism on top of this matrix, which yields some random permutation inside, which could disturb your distribution. So either you do everything conditioned on the distance matrix, which is fine, or you have to take into account this additional randomness.
This is exactly the nice point of this approach. You are perfectly right. But from the central limit theorem point of view, the results could be derived conditionally. So if you work conditionally on the axis, then you fix this matrix.
Yes.
That's clear. But where the problem comes in is in this supremum. Here you have to take into account all the permutations, and these permutations are random, I completely agree. And here comes the nice thing. The nice thing with this approach that combines near neighbors and projections. In fact, the number of situations is very, very well known. Because when you have 3 points, and you take a direction, this induces an order. You take another direction. This induces the same order. You take another direction. This induces the same order. So from the very beginning you feel that this continuous supremum in fact is discrete. And this is a very nice result of combinatorics, which tells you the following. It's due to a paper of Cover in 1967. And Cover says the following thing. For any collection of points WM in RP, and any permutation, you take we say that gamma induces an ordering, phi if you have something like this. P is a permutation of the indices. What Cover says is that whatever the gamma is in the whole space, the number of permutations you may have here is given, and you have the form, the exact number of them. It's given by this lemma. The total ordering possible is given by Q and P, and it has this form. So you replace immediately this supremum with a supremum on a finite, a discrete set. And you know exactly how many they are. At most it's very rough. It's a very rough bound, but it's okay. Because when you get an exponential bound, take the logarithm of this, it will be peanuts.
Usual payment for this.
The log times p. You see the p coming in front. Times p. You cannot get rid of this because you have np here. So certainly you cannot improve p. But what is very interesting is that you don't need to study this statistic here. You only needed to study it for one fixed gamma, so it's no longer a process, it's only one statistic. And for this you have very powerful tools of concentration. And then you use the very trivial inequality that the probability of the union is smaller or equal than the sum of the probabilities. And that's the story. So no U process theory, no entropy, nothing. Only orderings. Of course. But not the usual entropy. Very basic entropy based on orderings.
There is just the entropy of the sphere.
Yeah. But not VC classes, not things like that. Maybe they're behind, but similar arguments. This was very funny to see how it works. So with this at hand, then you have, just to show you, you have concentration inequalities like this kind.
Maybe this has to do with, because like when you do ordering with statistics, this transform, this is like distribution free, what you get, so
Yes.
C class sacrifice to combinatorial.
In some sense, yeah. Becomes distribution free, only the count points. Because don't care about distribution. And this is very nice. The technical conditions behind that are much lighter. All these technical conditions you saw in the previous approach, I don't have them. I don't need them. Because everything becomes distribution free. So for your statistics, you have inequalities of this kind, where A, B, C, D are norms of the matrix. You see the supremum, the norm on the rows, the Frobenius norm, and this is the kind of spectral norm. And these results are available for your statistics, not for your processes. And then it's enough to apply it to our story, where this is the matrix, and here are U, I, U, J truncated to M, and Z is a random variable that has the law of U given all the x's. This is a random variable that has the conditional law of U given the x's. So you apply, of course, with this truncation, because the U statistics are, inequalities are for bounded variables, but then you control the tails by this power 11, yeah? Story, and by some moment conditions. So it was quite nice to see that projecting on the line and using this combinatorial idea, finally you get, in some sense, simpler results. Okay. So that the central limit theorem and this are conditional, so it will not be a problem to derive. Well, I will finish with some numerical illustrations to see that it really works. We took, I did not do it, just my co-author from Spain did it, but he's very skillful, and I think it should be correct, or everything he did, and the results are quite interesting. He considered x to be a Brownian motion on the unit interval, and u, it was either a Gaussian, so no influence of the axis, or something alternative, a linear dependence, with b the coefficient that you see here, and epsilons are normal 0 sigma squared, with sigma 1.219. Why all this? To follow simulations done in the literature and to be exactly in the same type of framework. For instance, here to have a signal-to-noise ratio that is 0.1. And the third scenario is a quadratic alternative of this kind with h a constant. So he considers this, and he tests for the effect of x. U is scalar here. So x was decomposed in the usual way, the usual sign basis of the current and log basis, and the sample size was 100 and 200, and the experience was repeated 1,000 times. So what we have here? Well, here we have, so P, remember number of projections, 3 and 5.
So it's not automatically chosen.
We had no, for the moment, we had no criteria for P. P, 3 or 5. Well, there are so many things inside, we cannot do everything. We will try, but yeah. Already there are two approaches here with nearest neighbor and smoothing, and yeah, maybe we'll continue for a P. But this, even for estimation, the choice of P is delicate and depends. Some adaptive procedures are certainly needed, but well, you have so many things: P, alpha, and H, so many things to choose. There is so much work to do. But let's see how it works in this very preliminary setup. What we put here on the last column is a test that is specifically designed for linear alternatives. We call it CT test. It's a paper of Cardot and co-authors. And this test is a Fisher type test. You just decompose B in the basis, you stop the basis, and you check the nullity of all the coefficients that you truncated. This is a basic Fisher test. So it's very powerful against linear alternatives and clearly may not detect quadratic alternatives. And this is exactly, this intuition will be is what we will find in the simulations. So here is under the null hypothesis for different choices of CH is a constant that multiplies n to the power 1/5 or 2/9. I don't remember. Well, one of these powers of n. So you have different bandwidths, and here you have the two estimators, the one with a projection and the one with I think with the non-parametric estimate. This here. V and square. So for the levels under the null hypothesis, no problem. And of course we use bootstrap to correct for the level. Here we are under the alternative, linear alternative. The rejection probabilities are the highest. The rejection probabilities are the highest with a parametric test, with a Fisher test, which is quite reasonable. And here you have the rejection probabilities with our test for different bandwidth choices and different sample sizes and the two estimators of the variance. And for p equal 3, p equal 5. Here, what we took is what we call the best direction. What is the best direction was a projection of the b vector in the basis. The first component of the projection of the b vector in the basis. This would be the best direction because we go in the direction of b in some sense. And here what we call a worst direction is something orthogonal on the best direction. So when the initial guess of gamma is in the direction of the alternative, you expect good power, and this is indeed the case. And when the direction of gamma is not informative with respect to the alternative, which is the case with an orthogonal direction, then the test should have less power. Is still consistent because you optimize on all directions, but since you guide it at the beginning in the wrong direction, it should less intuitively you should get less power, and this is exactly what we observe here. You have less power, the probability of rejections here are low than there. Of course, for the last column is exactly the same because it is exactly the same test. Now, when we go to the quadratic alternatives, we took the quadratic alternative in such way that the expectation of x delta x is 0. In other words, the alternative is orthogonal on the mole, and the Fisher test will not see it. By definition. So, indeed, the Fisher test do not see the alternative. So the test will not tell you that you are under the alternative. But the other tests we propose, the tests we propose, do realize that it's an alternative, quadratic, not linear, but it's an alternative. And you see the rejection probabilities. There is some sensitivity with respect to the bandwidth, and less sensitivity with respect to p. So there is some work to do. I completely agree for the choice of the h. There is some work to do. This is for sure. Here is a first eigen function in the decomposition of delta square, and here is the second eigen function. So this should be more favorable to detect than this one. I think it's okay. I finished. Thank you for your attention.
Okay, let's end Valentin.
Now, if you have questions, we can talk for some. Not too long, but.
Well, we're still more or less in schedule. Questions it was very informative, impressive, and stimulating series of talks. But so there is now I am informed the slides are on the web of our lab. It's also distributed manually, but Valentin is available anytime. And here in red we know how to reach him. So just what I would like to say, you see there is open possibilities of discussing, of cooperation, and so on. And if any of you find the topics interesting, so this can be developed and extended. At least there is a started cooperation with Valentin in our our group, and we discussed different issues mentioned here, choosing P, choosing H, doing everything non-asymptotically, and advanced concentration inequalities for quadratic forms could be also an issue.
I think this nearest neighbor approach is very promising because finally it's just discrete optimization.
I mean, you have so gamma on the sphere, so what you get at the end is the entropy of the sphere. So I mean, even if you use empirical processes, it should give the same answer.
Well, the available results for your processes, you've not been here, but the available results on your processes, I mean, the sharpest I could find is here with p to the power 3.5. While this combinatorial idea gives you only p.
And so we started to discuss the story about the supermode quadratic forms with respect to the parameter. And so if it works to reduce to linear functional, then you know it for the entropy. Which matters. So in this sense, I'm relatively optimistic that it works. So, just to mention, once again, so the invitation was not occasional, so it's exactly in the flavor, so this is very close to our own research, and therefore would be very useful to see how people are working in this area, and finally to understand how we will work.
To improve things, yeah?
To make it properly.
Okay. Is this recorded?
You will get the film.
Okay.
Okay, any other question? So enough information, then let's thank Valentin once again.
Thank you for being here. Thank you for your attention.
Okay.